All right, we're going to take a look now at the beginning of our new unit about number patterns and generalizations. And today we're going to look primarily at the terms you need to know and some of the notation. This is going to be quite a few notes, so make sure you get your notes ready, pause as needed to write everything down. Basic vocab, sequences are lists of numbers in a certain order. The order does matter, following a specific rule, and a series is when you add those together. So if we take a look at these examples here, this is a sequence, and these are both series. Okay, so they do have a fixed order. Series are being added, and the sequence is just a list of numbers. Finite, infinite, you've heard those terms before. A finite sequence or series has a fixed number of terms. This one ends, this one also ends, and this one is infinite because it goes on and on forever, indicated in this case by the ellipsis. So this is an infinite series. This is a finite series, and this is a finite sequence. You can pause it as needed to write down all of those notes. We're going to specifically look at two types of sequences and series. As you see here, it is possible to be neither of these, and many are. We're going to look at arithmetic ones, which is where the same value is added or subtracted. Those are the same thing to get from one term to the next. And geometric, which is when each term is multiplied, or if you want to think of it as divided, depending on what it is, by the same value to get to the next term. This is called a common difference, right? Because when you subtract, the answer to that is called a difference. And this is called a common ratio. So in this particular case, if I'm looking for the pattern in the sequence, I'm adding 4 each time, plus 4. So the common difference is 4, etc. And it has to be for every single one. So this is arithmetic because we're adding 4 to each term to get the next term. This one right here, I'm adding 3, adding 5, adding 7. So it's not arithmetic. Multiplying by 4, multiplying by 9/4. So those aren't common differences or common ratios. This is neither. I do recognize a pattern though. I think I spelled that wrong, but 1 squared, 2 squared, 3 squared, 4 squared. It is a pattern to recognize, but it's neither arithmetic nor geometric. And this one is geometric because it has a common ratio of times 3 between every term and the next one. So this one would be geometric. Pause to take notes as needed. And here's the notation that we're going to be using a lot. U sub n means the nth term, the value of the nth term. So in the sequence -3, 1, 5, 9, 13, which we saw as an arithmetic sequence, it's saying what is the value of the fourth term, U sub 4. And the fourth term, first term, second term, third term, fourth term is 9. So U sub 4 equals 9. And U sub n minus 1 means the previous term. So, I mean, it's pretty easy to see. If n was 4, and I take away 1, U sub 3 means the third term, which is 1 before the fourth term. So you can use this notation to represent the previous term, which is important for when you have a recursive formula. A recursive formula is given by saying the first term, so where do you start, and using the previous term to find any term after that. So where are you starting, where are you going? They're often easier to write. And then the general term, it's a formula where you can find any term without knowing the previous term or any specific term. So for arithmetic and geometric, we have nice little formulas for those in your formula booklet, but they're not all that hard to derive, and you've seen a lot of them before anyway. We are only looking, obviously, at natural numbers for the number term. We can't have like the 1.5 term, but of course the value of that could be negative or rational or whatever else. So here's a simple example. Write a recursive formula and the general term for the sequence. It's arithmetic because I'm adding 2 each time, common difference. So recursive, remember that a recursive formula, we need to define the first term. So the value of the first term, U sub 1, is 8. And what we have to do to every term to get the next one is I'm adding 2 each time. So to find any term, I take the previous term and I add 2. Okay, quite simple. Make sure that u sub n, the n or the n minus 1 are subscripts. They're smaller and lower. You wouldn't want to get confused and say that this is u sub n and then bigger, minus 1 plus 2. That's obviously something different. And the general term, you see in this particular case, you do need to know the previous term. We're just adding 2 every time, but that's not great. If I said, okay, what's the 100th term? You would have to find the 99th term to do that and have to write them all down. But the general term is, you can think in this case like a linear equation. So the general term, if I wanted to say, okay, I can find the value of any term. This is my slope, really, for an arithmetic sequence. We can look at the slope, and I'm going to multiply it by the number I have. And again, we're going to work on this more in the future. This is just an example of the notation and the names we're going to do. If I want my first term, well, 2 times 1 is going to give me 2, but I need to obviously get to 8. And 2 times 2 for the second term would get me to 4, but I need to get to 10. So in this case, plus 6. Okay. If we were to look at this as a line, this would be the intercept, the y-intercept, which would be the 0th term, which we're not going to look at. We're only looking at 1, 2, and those natural numbers. So here would be the general term. And then quite simply, I could say, well, the 100th term, the value of the 100th term would be 206. So they both have their pros and cons. The last thing here is called sigma notation. Sigma notation is a way of indicating a series. Because what sigma, this is the capital letter sigma, what it tells us to do is sum up or add together. So this big capital sigma means the sum. Okay. And what it tells me to sum up is I'm going to start when n equals 1. Sometimes you'll see it with n equals 1 or whatever the variable is that you're supposed to put in. Sometimes it will look like you have multiple, but you're only substituting in for one value. It may define it. If it doesn't, like if it just says 1 to 5, then you would assume that it's the variable that's in here. So this is telling me to start, and then the top is going to tell me where to stop, counting up our natural numbers. So I'm going to start up when n equals 1 and put it into this general term. So 3 times 1 minus 7, and it's the sum, so I'm going to add it. And then 2, that's the next one. And the next one is 3 times 3 minus 7. I'm going to have to go to the next line. 3 times 4 minus 7. And I'm going to stop when I get that n is 5. That's the next one. You don't need to put lines underneath or any squiggly things. I'm just doing it to make it clear. So I started when n is 1, and I added up, like sigma tells me to, all the way until n equals 5. And then I just want to simplify this. So 3 minus 7 is going to be negative 4, plus 6, negative 1. That's 9. You'll see here what I'm doing is I'm creating this arithmetic sequence. This is a series, excuse me. 2, I'm counting up by 3s every time. This should be then 5. And this one is going to be 3 more, 8. Adding all those up, and we will have a formula. It's 10, 15, minus 5, 5. There is a nice way to do this in the calculator. I will show you how to do that when we're in class. It's really not challenging at all. And then we also have formulas to do this so that you don't have to write out every single term. Here's one example that looks quite messy. Write this in sigma notation. I would need to recognize a pattern. It's a series. I would need to make sure there's a pattern in order to write it like this. I see there's some number, some A's, some B's. It doesn't really matter. There are many different possibilities where we could do this. We could change this number. Like I could say start, I don't particularly want to say from 6 to 12 because I need to do every single one and I would skip 7. So there's some kind of doubling going on, like 2 times n will give me even numbers. Okay, and then if I wanted this to be 2 times n, that would mean I want n to start at 3. So this is going to give me all the right things. 2 times 3, 2 times 4, 2 times 5, 2 times 6. So I would want to stop when it's 6. And then I want to see how I can make the pattern work out. Well, 3, 4, 5, 6, let's just n. And this one is 1 more than that, so n plus 1. And this expression as sigma notation would be giving the same series. Okay. It's not arithmetic, it's not geometric. We can still represent it this way. It's just a matter of identifying patterns and seeing how we can write those using sigma notation. And again, as we go forward, we'll look primarily at arithmetic and geometric and the formulas that we are given.